Hi, today's topic is scaling limits of local extinction sets for critical branching processes with immigration. And this is joint work with my PhD student Ben Povar at Warwick and my long-standing collaborator Geronimo Uribe at UNAM. And most of it was done while Geronimo was a research fellow on one of these grants at Warwick. Okay, so we're interested in the Bienayme-Galton-Watson process with immigration, which is described by really two inputs. One is the offspring distribution, mu on integers, and one is the in-migration distribution, mu. So the process evolves. You start with some population, and then you take this IID double index sequence, which describes the number of individuals, descendants of the individual I, and nth generation, okay? And then in order to go from generation n minus 1, every individual in generation n minus 1, so z1 of n minus 1 of them, they have children, and you just add up all these children and you let's say immigrants. Okay, and this is a strong Markov process, of course, on this state space, and we will be interested. You will see why later in the critical case. Okay, so the supercritical clearly not interesting in this situation for zeros because it is going to be transient, and the subcritical case also doesn't play a role because of the scaling limits. But we're interested in particular also in the non-degenerate case mu, right? So in other words, not the case where every individual has exactly one child because then the process is constant. We are interested in the sort of local extinction set, so a set of this type, and for this to be non-trivial, we need to allow there not to be immigration from time to time, okay? If we have too many immigrants, then again the process will be transient. So we want to describe the scaling behavior of this quantity. So this quantity under this assumption will go to infinity almost surely, okay, and this should in some sense approximate the local time of the CBI limit. That's the idea. So the main question is there a scaling limit of this simple object, combinatorial object L1? And in fact, more generally, we're after a joint scaling limit. Okay, joint scaling limit for some sequences Bn and Cn. In order to describe or discuss this, I will first focus on this first component, which is, of course, a classical question: when do Bienayme-Galton-Watson process with immigration converge to CBIs? To tell you about Bn and then see the extension. Okay. Now, in order to understand the scaling limits for BGWIs, it's best to sort of rewrite it in terms of the Lamperti time change transformation, right? So this is my process in the dynamics that I discussed, but in fact, it has this sort of pathwise time change representation where x1 and y1 are two random walks, and the walk x1 has the law given by mu but shifted to sort of sit on -1 and all the naturals, while y1 is a random walk with increments given by the immigration. You see, and where this comes from is directly seen from this representation, right? Because the increment of my population really is everybody in the population has children and has this many children, right? And then they still cease to exist, right? So I need to subtract 1 from that sum, and that's exactly the increment of this walk over the time interval given by the size of the population. Now, mu is critical, so this walk will be a martingale random walk, okay? It's going to be downward skip free, of course, because every individual can only not survive itself. But of course, Z1, many individuals cannot survive in one step, have no children, so Z1 is not downward skip free, and that's also relevant for this story, as you will see later. And this guy has increasing trajectories. And now, the idea is, okay, x1 and y1 have scaling limits. Let's say that in domains of stable attraction, then z1 should be in the domain of attraction of a self-similar CBI. But of course, this is not in general true because these two guys need to be sufficiently balanced so that we can scale in a balanced way so that neither reproduction nor immigration dominate. And of course, this is described by this classical assumption SL, okay, which I will now state. So it most easily stated in terms of the generating functions. Okay, I take the generating functions of my immigration, of my reproduction, offspring, and immigration distributions, and I assume that f takes this form, which means s plus 1 minus s to the power 1 plus alpha times some slowly varying function, and g, the immigration generating function is of this form, and now the balancing that I mentioned earlier is seen in the fact that this guy is going to be in alpha stable domain of attraction, while this guy is in 1 plus alpha stable domain of attraction. And also, it's more subtle than that. You need to balance the slowly varying functions, okay, in this way. And it turns out that this guy, this assumption, is equivalent to mu being critical, to x1, the walk that corresponds to mu tilde, being in the stable domain of attraction of spectrally positive stable Levy process of stable process of index 1 plus alpha, and this stability in the slowly varying function is translated into the stability of the tails of the two distributions. And now, so in particular, you see that this guy is also going to be regularly varying. The tail is regularly varying of index 1 less, and it's going to be in the stable domain of attraction of alpha stable subordinate. Okay. And then under those assumptions, x and y, the random walks converge. Okay, under the correct scaling, and the scaling is sort of the scaling that makes y1 get into the business of into the stable limit. And this Bn, of course, is really a solution of it's an asymptotic inverse of Bn of x of a function x to the alpha divided by L of 1 over x. You see, but because L and K have the same asymptotic behavior, it doesn't matter whether I use L and K when I look at these asymptotic inverses. And then, in fact, assumption SL is equivalent to this convergence happening, weak convergence happening on the level of, so this BGWI scaled in this way converges to this CBI that also has this representation where X is spectrally positive, alpha 1 plus alpha stable. Levy process in this guy is a stable, alpha stable subordinate. Okay, so that's the setting. And now, okay, that's my assumption. And now what's our theorem? What's our actual result? Well, we identify the scaling for the local time and prove that the weak limit holds under the same assumptions. Okay, let me just now parse this a little bit more slowly, right? So I assume the assumption SL holds, which I've written here, and then I construct this constant delta. This is D over alpha C, right? So this D, alpha, and C, okay, depends both on the immigration and reproduction laws, and I assume that this is between 0 and 1. And in that case, the probability of local extinction multiplied with n is going to be proportional, is a regularly varying sequence of index 1 minus delta. You see, this is positive, so this Cn will go to infinity. And this is exactly the scaling that is required to get my local extinction set to converge to the local Markov local time of the self-similar CBI of index alpha, which is obtained by really from this time change equation where the x is spectrally positive index alpha stable Levy process and y is a stable subordinate. Okay, and this Bn is exactly as it was before. So that's the main theorem that we prove. Okay, that's the main theorem. Now, let me just make a few comments on this theorem. Now, of course, the first simple thing to note is that this Cn is done by, you see, is given up to this constant, but of course also the definition of local time is up to a constant. The Markov local time of the CBI Z, or self-similar CBI Z, is also up to a constant. So you fix one, you get the other, etc. Now, this assumption, the delta is between 0 and 1, is actually necessary. And the reason for this is because this delta greater than 1, greater or equal to 1, Z is not point recurrent. I mean, the way to think about this, right, is in the special case of typically finite variance when alpha is equal to 1. So in that case, my limit, my Z, is just going to be proportional to square Bessel of dimension 2 plus delta. You see, when delta is greater or equal to 1, 2 plus delta, 2 delta is greater or equal to 2, and 0 is polar, right? So I don't get a non-trivial local time. So this is necessary, and this theorem, of course, covers the entire domain of attraction of offspring and immigration laws when alpha is between 0 and 1, and these are all going to have infinite variance. Okay. Now, we also cover all finite variance offspring laws, mu. Recall that this mu is finite variance if and only if the second derivative at 1 of its moment generating function is finite, which is equivalent to alpha has to be 1, because alpha is smaller than 1, it's not going to be finite variance, and the slowly varying function has to have finite limit. Okay, and because of these balance conditions, this means that in this particular case, the immigration has to have finite mean also. However, there is also this interesting case where alpha is 1, but the reproduction mechanism has infinite variance, and but the scaling limit is still a continuous CBI, in particular proportional to squared Bessel of dimension 2 delta, right? And the convergence still holds. And now my final point about the theorem is that this convergence actually, even though it looks quite robust, is very fragile, of course, because we're dealing with local time, right? So you see, I take some mu and nu where the assumptions hold, and I perturb it only a little bit. So what do? I change my immigration so that I reduce the amount, the probability that there are no immigrants, and I keep mu exactly the same everywhere else. This, of course, is not going to perturb this convergence, because this convergence is all to do with tails, right? So this is scaling limit. I will still get a nice self-similar CBI in the limit. But whatever sequence Cn prime I choose, this counting local time will not converge to L. This is simply because L is a non-trivial really range of a 1 minus delta stable subordinator, while this guy will sort of converge to 0. It stops happening because there is smaller and smaller probability that there are no immigrants, right? So there's always, the process always gets a push, so the excursions become slower and slower and eventually stop happening when I go down along the sequence. Okay, now one of the easy implications of our theorem is this septuple limit theorem, right? Because you see there are some natural quantities here, right? In my Lampertis discrete time change representation, I've got the time change of my random walk that represents reproduction, I've got the immigration, I've got the time change itself, and I've got the local time of this guy. This x1 is sort of skip free, downward skip free. It has local time, or counting local time at 0. L1 has a local time, and it turns out that all these quantities converge to the corresponding quantities of the time change representation for the self-similar CBI, right, where x is, 1 plus alpha spectrally positive Levy process, and y is an independent alpha stable subordinator. Okay? So these are the local times, and this is the limit theorem. This is the limit theorem. And you see, in this limit theorem, what's interesting, all these 7 quantities will converge, and there are 4 different scales, okay? So the scale Cn is for the local time of Z1 that comes from the theorem. Bn is the scale for Z1, it turns out. Of course, this quantity will have the same scale as Z1, and so will y, right, of course. Now, this C1 is actually an integral of Z1, so it'll have a scale, this guy has a scale Bn, this guy will have scale NBN. Now, because this guy has scale MBN, I need to scale x1, speed up x1 at this rate, and it turns out that then I need to scale it, of course, as Bn, so these things sort of match. The most interesting scaling is this scaling here, which is the scaling of the local time of x1, and it turns out that we prove that this alpha n is a regularly varying sequence with index 1 plus 1 over alpha. Okay. Now, septuple theorem follows from the main limit theorem, as clear, and from the stability of the time change representation of CBIs, of course, which is well known from this paper, and the invariance principle for local times that Geronimo and I established not so long ago, but here applied to the skip-free random walk x1, and this application is not hard. Now, how does the proof of our main limit theorem work, right? Well, our main limit theorem is really a consequence of this invariance principle from a couple of years ago, applied to Z1. And this is a general result for regenerative processes, and it turns out that the application to this setting is highly non-trivial. And in fact, what we do is we present a paradigm for the verification of the assumptions of this invariance principle that we hope will make it much more broadly applicable than the actual examples in this paper. For example, to reinforce random walks or random walks in random environment, etc. And I will devote the next video actually to discussing this paradigm and showing how these things work. But one thing to say is that in order to make it work, one needs to use, of course, the distributional properties of Z1 as well as its pathwise properties. And we will, this in the case of BGWIs led to many new and what we found interesting results in the case of infinite variance reproduction mechanisms. Okay, thank you very much for your attention. I hope to see you in the part 2 of this video. Bye.